All right, so it is 3:30. We can go ahead and get started. Cool. Yeah, I mean, I think everyone's probably aware at this point we have about 2.5 weeks left until the end of the semester. So I don't know about you guys, I'm pretty excited. Sent out an email yesterday. We got that. I posted the solutions to the practice test, and yeah, I would definitely suggest, going through those practice test solutions, very carefully. And I think it's going to be especially important for this newer content that we're going to be learning over the next 2 weeks. So, like I mentioned, the final exam, it is going to be the last day of class on Tuesday. It'll be, at 3:30. I I'm gonna get a room. I think I've got a room set up. So I'll let you know where the room is located in an email today at some point. So we've got that room all set up. So again, it will be April 30th from 3:30 to 4:50 in that specified location. Like I mentioned, you can use a cheat sheet. You can write on the front and back. You can write, whatever you want. The only stipulations is that it has to be on a standard, 8.5 by 11 sheet of paper. Everything has to be handwritten in your own handwriting. And you can't have anything printed off on that sheet of paper, essentially. And yeah, basically the exam is going to be on units 1 through 15. So what we're going to be doing today is wrapping up with just the final, pros and cons of Gaussian mixture models. And then we're going to be moving on to those additional 3 units of content, which will also be on the exam. So we're going to be talking about Birch as well as mini batch k-means, which are going to be, 2 new clustering algorithms, but they're going to be, what we call online clustering algorithms. So these are clustering algorithms which are specifically designed for the purpose of big data in mind. So they're pretty cool. And then the final clustering algorithm that we're going to be talking about next week is what we call spectral clustering. So this spectral clustering is a useful algorithm when it can actually be used to cluster different types of data. So you can use it to cluster a standard tabular numerical data set. And one of the benefits of spectral clustering is that it's going to be another clustering algorithm that you can use in your toolbox to identify non-convex clusters. So that's one benefit of it. But then additional benefit of it is that it's an algorithm that can be used when you're trying to cluster graph-based data or network-based data. So for instance, if you have a social network and you want to find highly dense connected clusters of socially connected people, spectral clustering is an algorithm that can essentially do that for you. So yeah, cool stuff. So that's basically what we have coming up. You want to make sure that you're declaring your groups pretty soon. I think I set the group declaration deadline to be the 25th. Again, if you're having any issues finding a group mate, let me know. But do make sure that you're signing up on that Google spreadsheet so I can get a sense as to how many presentations that we're going to go through on that final presentation day. But yeah, that's basically what we have coming up. So any questions for me before we get started? No? Okay. Like I mentioned, we talked about how to apply Gaussian mixture models to the MNIST data set on Thursday. So the final thing that I wanted to wrap up with Gaussian mixture models is just some of the benefits and drawbacks. So, like we mentioned, Gaussian mixture models, and in particular using the EM algorithm to help us maximize the log likelihood function value of our Gaussian mixture model PDF. The algorithm that we use to, attempt to find the optimal solutions to the log likelihood function value is actually, as we discussed, a generalization of what we were doing in k-means and fuzzy c-means. But the benefit of Gaussian mixture models is that we are making a much more flexible set of assumptions about the nature of a cluster. So in Gaussian mixture models, we can actually Um, the Gaussian mixture models is actually well suited to identify clusters that are not just spherical in shape, like k-means and fuzzy c-means, but it's also designed to detect clusters that are ellipsoidal in shape as well. Now, one of the additional benefits of Gaussian mixture models is that it's a much more rigorous, statistically rigorous technique. So it allows for us to essentially calculate the probability or the PDF that would have generated theoretically the data set that we're actually observing in the data set that we have in our hands. Or in other words, it allows for us to estimate the random process which would have generated that data set. And so oftentimes, like a lot of data sets that we end up using are assumed to have been generated by some sort of random process. So the nice thing about Gaussian mixture models is it allows for us to, come up with a formal model that, approximates that process. And then with this statistical model that we end up fitting, it allows for us to not just cluster the data, but it also allows for us to use the assumptions about how our data set that we actually have was generated. It allows for us to use those model assumptions to generate new observations, that would have come from that data set, from that same random process. For some reason, my pen is not working right now. That's not good. In addition, it also allows for us to estimate not just the means or the centroids of our clusters, like in k-means and fuzzy c-means, but it also allows for us to estimate the covariance matrices of each of the clusters, as well as the priors, i.e. the probability that a given observation was randomly drawn from one of the K clusters in our data sets. Now, the final benefit, you could think of this as a benefit, but you could also think of it as a drawback as well, depending on your particular research goals. So unlike fuzzy c-means, Gaussian mixture models does not allow you to pre-select the overall fuzziness of your fuzzy clustering membership scores. So if you didn't really want to think, if you didn't want to think about, what would be the best fuzziness parameter, if you didn't want to have to perform parameter tuning, Gaussian mixture models might benefit you. On the other hand, if you knew that, for instance, based on what you were seeing in your TS&E plot, that, there was a particular level of fuzziness that you felt should be reflected in your fuzzy clustering, then this can also be a drawback as well. So essentially what we ended up seeing in our Gaussian mixture model clustering of the MNIST data set is that we actually simply just ended up getting a very hard assignment, of our observations to basically one and only one cluster. And this can, so basically it didn't really reflect any fuzziness. It didn't really reflect any uncertainty about, which cluster even the straddle nodes should have belonged to. So it didn't really reflect that relationship that we essentially saw suggested with the TS&E plot. So we might have been essentially losing some of that useful information. And in addition, that can also be, for instance, like if you run a fuzzy clustering algorithm like fuzzy c-means or Gaussian mixture models, and you end up getting a mostly hard assignment, well, not only do you kind of lose potentially useful insights about the nature of straddle nodes, for instance, but another potential downside is that unfortunately, these Gaussian mixture models, so the EM algorithm used to fit a Gaussian mixture model, is more computationally complex than fuzzy c-means. And then we also saw that fuzzy c-means is more computationally complex than k-means. So, if you knew ahead of time that you were simply just going to end up with a really hard assignment, then, practically speaking, it would probably have been better to run k-means, given how hard of an assignment, your particular Gaussian mixture model clustering ended up being. And then some other downsides of Gaussian mixture models is that, performance tends to suffer, especially when you have clusters with a small number of observations in them. Performance tends to suffer when the observations in your data set are highly collinear. And much like we saw with, k-means and fuzzy c-means, the algorithm tends to be sensitive to noise and outliers as well. And then one final downside is that, if you're using the EM algorithm to attempt to, find the optimal posteriors as well as the optimal um, parameters for your Gaussian clusters. Unfortunately, this algorithm is not guaranteed to converge to a local maximum of that objective function. So for instance, it could unfortunately converge at a saddle point solution like that, as opposed to a local maximum, which is what we're attempting to achieve. So something to keep in mind. Okay, so they're basically just wrapping up with some pros and cons of the Gaussian mixture model algorithm. But yeah. All right. Any questions on that? Okay. Okay, cool. So you might notice I'm talking a little bit faster. So there is, there's 3 more units of content that I want to get through. So I do want to make sure that I have time to get through all of them. But again, if you have any questions as I'm going through this, please don't hesitate to reach out. Okay. All right. So moving on, we're going to talk about 2 types of what we call online clustering algorithms in this class. Now, the online term is actually not simply just a term that's applied to clustering algorithms. There's actually many just general online machine learning algorithms in general. And we tend to talk about online algorithms, especially in the presence of really large data sets, number one, but also number 2, in the presence of intermittent data, or in other words, data in which we don't actually have the full data set in our hands at any given time. So, these can be situations in which you have data which is, constantly coming in that you would like to constantly update your algorithm with. So this is a situation that I ended up seeing, when I was working in online advertising, for instance. So for instance, suppose that you are a data scientist that works at an online advertising company. And then, the clients that solicit your services are like large corporations, like a Coca-Cola. And then basically for each of the, ad creatives. So like, this is like when you click on a website, this is like, what you end up seeing. This is like an ad creative, if you will. And so basically like if, once you click on a website with a particular, ad, placed on that website in a particular location. I believe unless you select some sort of option, that online advertising company is in fact collecting information about some aspects of your viewing activity. So for instance, these companies can collect a variety of certain types of information about your activity. So for instance, let's just say they had collected, the amount of time you spent on the website, how many links on the website that you visited, some metric for scrolling activity. So let's just say if you're the data scientist and you'd like to, cluster this data set here. But for instance, suppose it's the case that every 10 seconds, you get a new batch of about 10,000 rows of data. So you'd like to cluster this data set, but as we can see, we're probably going to run into a couple types of complicating issues here. So what are some issues that we might encounter in this scenario that I just described? So let's just say I wanted to use k-means to cluster the data coming in. So what are some issues that I might encounter? Yeah, exactly. So we want to think about how to find a way to add new data without having to rerun the algorithm every time. Yeah, so that's what we just expressed there. That is an issue of intermittency, right? So given that new batches of data are perpetually coming in, we'd want to think about questions of, for instance, when to stop collecting data and actually run the algorithm. And then, we'd want to ask the question, do we even want to stop collecting data? We'd want to think about, is it possible for us to just cluster a portion of the data set and then iteratively add new observations to the clustering without having to rerun the whole algorithm? Okay, well, that's a relevant question that we could ask. So in the question of, is it possible for us to, be able to just get by clustering a small portion of the data and then, iteratively, cluster new observations as they come in without having to run the whole algorithm? Well, that's really going to depend on how representative our first few initial batches really were. So for instance, let's just say we decided to stop collecting data at 1 million, 1 million observations. And we said, okay, that's enough. And so, what we could do is we could collect those first 1 million observations and, with k-means and find, a particular clustering structure. We could calculate the centroids of those two clusters that we found, and then provided the new observations that kept coming in were representative of the clustering structure that existed in the old observations, then we could theoretically expect relatively good results if we simply just took those new observations as they came in and simply just assigned them to the closest existing centroid of the old clusters. Okay, so in a scenario like that, we might expect to get pretty decent clustering results with out having to rerun the whole algorithm. On the other hand, though, it could entirely be possible that the first few batches of data were not necessarily representative of the full data set that we would eventually like to cluster as new batches came in. So unfortunately, in a scenario such as that, if we were to assign each of our new observations to their closest centroids, then we could end up getting a clustering, a k-means clustering, if you will, which is markedly worse. Or in other words, it fails to identify the inherent clusters that actually exist in this full data set that we would like to cluster. That would be something that we would want to consider. So, the situation is, unfortunately, if we have data sets can change over time, new clusters can form. And so the likelihood that, our first few batches is going to consistently remain representative of all new potential batches that could come in, especially in situations like these, is unfortunately it can be a bit of an unrealistic assumption. So because of that, we want to be able to design clustering algorithms which can, one, iteratively adapt the nature of the clustering structure, but number two is not going to be as bound to the clustering structure that was, essentially observed in the first few batches. So that's going to be one of our wish list goals for these two new online clustering algorithms that we're going to be introducing this week. But now let's just say, for instance, it was a scenario in which we had, our old data set was more or less guaranteed to be, to have the same clustering structure of new batches of data. And so let's just say, for instance, we decided to stop collecting observations once we had 10 billion rows. So what's another issue that we might encounter? Let's just say we wanted to use k-means clustering to cluster 10 billion of these rows. So what do you think? Is k-means going to hack it? But let me ask you this, like, so what if I gave you a what if I gave you a CSV file with like 10 billion rows and you tried to cluster it with k-means in your Jupyter notebook? Let me ask a poll. Okay. Who thinks that you'd be able to do this successfully? Okay. Yeah, so I will also say, yeah, you're going to run into a lot of problems if you were to attempt to do this using the basic k-means function. But even before you got to the aspect of, or the part of the analysis in which you were using k-means, you're going to run into an additional computational issue as well. So number one, I can tell you right now, if you try to load a data frame with 10 billion rows into your Jupyter Notebook environment, it's going to crash your kernel. So the task of loading, say, a data frame of 10 billion rows into your computational working environment may be infeasible. So the task of loading the entire data set, if you want it to be large, is going to be problematic. And then in addition, while k-means tends to be one of the fastest clustering algorithms, it does not hold up, unfortunately, against really big data sets. Okay. So, k-means used to be a pretty good clustering algorithm when it came to large data sets. But, as the amount of data that we can collect on any particular scenario is computationally exploding, we need to design even more effective clustering algorithms, which can handle, even larger data sets. So this is going to be another reason for why the two online clustering algorithms that we're going to introduce in this week are going to be useful. So these techniques that we're going to be introducing, so Birch in this unit and mini batch k-means in the next unit, are two types of what we call online clustering algorithms. So these are clustering algorithms in which the data becomes available in a sequential order and is used to iteratively update the clustering with each new incoming data point. Okay, so it's going to be clustering algorithms of this nature are going to be much more beneficial for this situation here. Now, this is different from what we call batch clustering algorithms. So basically, all of the clustering algorithms and all of the algorithms in general that we've introduced in this class so far are what we call batch algorithms, in which it's assumed that we generate results or generate a clustering by using the full data set all at once. Okay. So as we've seen, if it's impossible for us to load a full data set all at once into your Jupyter notebook, then we're going to need to rely on these online clustering algorithms so we don't essentially crash our kernel. So some common goals of online clustering algorithms in general are ones in which you're trying to essentially minimize your input-output costs. That's one thing that we're going to be thinking about as we introduce these online clustering algorithms. In addition, we're also, we're specifically designing these algorithms in mind, where we're trying to minimize the total amount of data that needs to be stored in your memory at any given time during the algorithm. So we're, these algorithms are explicitly designed with memory in mind. And then in addition, it's also thinking about how do we minimize the overall amount of time that it takes to cluster these large data sets. Okay. And then generally speaking, just the general, assumption about these online clustering algorithms is that, regardless, you don't actually need to use the full data set, or you don't actually need to have the full data set loaded in your working memory to actually cluster that full data set. And so one of the benefits of Birch, the first online clustering algorithm that we're going to introduce, is that it is going to be somewhat similar to k-means. So we are going to see similar clustering structures that it is both able and not able to essentially cluster. And the reason why is that, this is not, what you're going to see is that the Birch algorithm is very different in terms of how you actually execute it from k-means. But the similarity is going to be the distance functions, as well as the ways in which we measure cohesion of the clusters. So these cluster cohesion metrics are actually going to be the same way that we measure cohesion in k-means, essentially. All right. So to contrast, to really showcase like why Birch is, more beneficial or better, I guess you could say, than k-means in terms of how much memory is required to essentially run k-means. We want to think about essentially what information do we need in our working memory at any given time to run k-means, or in other words, to execute a given iteration of k-means. What data do we actually need to have loaded, if you will? They want to remember k-means. Yeah, so we need to have two things. So in any given iteration, we need two things. First, we need the current centroids, right? And so that would be if we have k centroids, each with n attributes. So it essentially would be comprised of a k by n matrix. And then what else do we need in a given iteration of k-means? Do you remember in k-means we have the cluster assignment step, and then we also have the centroid update step. So for instance, in the cluster assignment step, right, we go through each of our observations and we assign it to the closest centroid. So given that, what else do we need in our working memory to execute that iteration? So the data, so the distances between the centroids and the observations. Yeah, so that is something that we would need to calculate for sure. But I think what I'm trying to get at here is that we would actually need to have the full data set X itself, right? So in any given iteration, there's no way that we can't like take a portion of our data set and just kind of put it aside. In order to, reassign every observation in the data set to a given cluster, we actually need to have every single one of those observations in the full data set X itself. So because of that, at any given time or at any given iteration, k-means, we would also need to be storing our m by n matrix X. Right? So, if we happen to have a really large data set, if we have a large number of rows or large number of columns, this, needing to actually store this really large data set in and of itself is going to be a problem. So one of the benefits of the Birch clustering algorithm is that it actually needs to store way fewer things in any given iteration of the algorithm. So what we're going to introduce, or what we're going to talk about, is that essentially what we're doing when running the Birch clustering algorithm is that we are building a tree. So we call this a CF tree, a clustering feature tree, which stores just a few pieces of information about a cluster or a subcluster that has been essentially incorporated into the given clustering structure. So essentially what this CF tree does is it keeps a very efficient, very memory efficient representation of the current clustering structure, which has been identified given the current set of observations which have been incorporated into the tree. So what we're going to see is that basically, what this tree essentially is going to be comprised of is a series of these CF, or these clustering features, which correspond to a given subcluster. So basically, if we've identified K subclusters that exist overall in the overall clustering structure that we've identified, then actually essentially the only thing that we need to store, or that we're storing in our working memory, is 3 times K observations. So the cool thing is that this clustering feature is essentially just a tuple that is always comprised of just 3 key pieces of information. And so with each of these clustering features, we can actually essentially identify all the important things that we would want to know about a given clustering without actually having to store all of the observations which have been clustered so far. So it's essentially the Birch or CF tree. It's a very efficient memory device that stores a representation of the clustering structure that we've identified so far. And so so basically this Birch CF tree, which we're attempting to build, it seeks to basically effectively help you identify the clustering structure while also taking into account 3 sets of constraints. So number one, we're directly considering how much working memory we actually have to store this CF tree. So one of the constraints that we have when building the CF tree is that the height of the tree can't get too large. So for instance, if the height of your tree gets too large, the algorithm restarts essentially, and it says, okay, let's change the parameters such that our tree does not go over our working, computational memory constraints. Now, another constraint that we have on the memory is essentially how many of these entries, these CF entries in the tree, a given node is allowed to hold. And so this is also taking into account how much storage your computational working environment might be able to deal with. But then we also have this additional constraint, which is more so designed to help you identify more compact clusters. So it's not just about memory. It's also going to be stipulating essentially, how spread out are your subclusters that you're identifying? How spread out are they allowed to be? So ideally, we'd like to identify, clusters of observations which are relatively cohesive. So we can set parameters in the design of this CF tree such that clusters like this would not be allowed because their radius or their diameter, as we're going to define, is essentially too large. So this is our overall goal of the algorithm. We're going to build this CF tree. This actually takes a long time to explain, but any questions so far? Okay. Yeah, so unfortunately, I'm probably going to be explaining this algorithm for the rest of the class. It is a pretty involved, lengthy algorithm, but it's super useful. So kind of bear with me here. So the Birch clustering algorithm, it stands for balanced iterative reducing and clustering using hierarchies. So as the word hierarchies would imply, is that you can actually use this or interpret this as a hierarchical agglomerative clustering algorithm. However, you don't actually necessarily need to use it as a hierarchical agglomerative clustering algorithm. You can simply just, if you if you had a sense that, for instance, there was like 5 clusters in your data set, you can simply just extract the clustering that has, 5 clusters and not necessarily even, observe the hierarchical clustering nature of the data. Right. So the input for this algorithm is the following. So this is basically designed, much like many of our other clustering algorithms, to only cluster numerical data sets with M objects and N attributes. Okay. Now, ideally, it is useful to know the number of clusters that you're looking for ahead of time. However, on the other hand, you can also use this as a hierarchical agglomerative clustering algorithm. So you can use the fact that you actually you can essentially find multiple clusterings that exist in nested relationships, and you can pick out, based on what you see in that dendrogram, you can pick out, what number of clusters might be ideal. Okay, so this is somewhat of a soft parameter that you need to pre-select. But the parameter that you do need to think carefully about selecting to some degree is this parameter T, which represents our diameter or radius threshold. Okay, and so what this threshold is going to basically correspond to is a measure of how cohesive we would like for our CF tree subclusters to be. Okay, so the way that we are going to measure the cohesion of a given clustering, there's actually 2 ways that you could go about doing it. You can either use the radius of a given cluster, or you can use the diameter of a given cluster. So in the example that I'm going to use in this, in the lecture notes, I'll use the diameter, but basically Python uses the radius. So scikit-learn birch uses radius. Okay. But what the radius of a given cluster represents, as we can see here in this equation, it's going to be a metric that is somewhat related to the inertia of a clustering, right? It represents the average distance each point is from the centroid of the cluster it was assigned to, right? So generally speaking, the lower the radius, right, the more cohesive the cluster. Alternatively, another way to measure cohesiveness of a given cluster could be to use the diameter. And so if we try to interpret this equation here, you can see that what this represents is the average distance, average pairwise distance of each set of points in a given cluster, right? So on average, the closer each of your observations are to each other in a given cluster, the more cohesive the cluster. Okay. So basically, the way that we go about building the CF tree is we assign iteratively a given observation to a given cluster, which we have identified in the current CF tree. And so, we have this additional constraint, when we're choosing to assign a given point to a given cluster is, we stipulate that, if we were to assign a given point to that prospective cluster, we essentially stipulate that the diameter or the radius, whichever one we're choosing to use, it's not allowed to go above a given threshold. So if the inclusion of that given observation in that prospective cluster would cause the diameter or the radius to go above the threshold, essentially what we do is we create a new cluster, which is based on just that new point, essentially. So that new point essentially forms its own new cluster. Okay. So as we're going through the Birch algorithm, we need to essentially always be considering how cohesive is a potential cluster. So we have our cohesion metrics, which we can see looks very similar to how we measured cohesion in k-means. And then in addition, we also need to, so basically when we're choosing to assign a given observation to a given cluster, we need to think about how separated two clusters are. So we also talk about measuring the amount of separation that exists between two clusters in Birch. So there's a wide variety of ways that you could go about doing this when implementing the Birch clustering algorithm. But the one that we're going to use is the centroid Euclidean distance. So basically what we're saying in this scenario is that the distance between two clusters, we're choosing to measure that as the distance between their two respective centroids. Okay. So given that, we're going to be heavily using these metrics for cohesion and separation that are heavily based upon the use of a centroid, we can already start to see that Birch is not an effective clustering algorithm for non-convex clusters, right? So basically the mean or the centroid or using the mean as a centroid, really only tends to be an effective way of measuring a central point of a cluster if that cluster is, convex essentially. So unfortunately, Birch tends to not work as well for identifying non-convex clusters. Okay. All right, I've been doing a lot of talking. Questions on that? Okay, so let's talk a little bit more about this tuple that we were discussing earlier. So the CF, the clustering feature. So for every subcluster that has been, or that is being represented by our CF tree, every one of those subclusters is always going to have a CF or a clustering feature that corresponds to it. And this clustering feature is always going to be this 3-element tuple comprised of the following 3 pieces of information about the cluster. So number one, the first observation or the first number in the tuple is simply just the number of the number of objects assigned to that particular cluster. So for instance, if this is our cluster here, the first observation in the tuple would simply just be 2 for 2 observations. And then the second value in the tuple is the linear sum. So we simply just take the sum of each of the attributes of each of the observations in that cluster. So the linear sum of this cluster would be 1 plus 3 and 2 plus 4. We get 4, 6. And then finally, the third element of the CF for a given cluster is the squared sum of the objects in that particular cluster. So we simply just square each of these elements here, and we add them up. So we end up getting 10 and 20. Okay. So the reason why we're using or calculating these 3 particular metrics for a given cluster in particular is because the clustering feature, these 3 elements, has these nice, useful properties, which essentially allow for us to quickly recalculate the relevant information for new clusters which have been formed by merging particular clusters together. So for instance, let's just say we had a particular cluster CK and a particular cluster CJ. So if we wanted to calculate the clustering feature of the cluster that we would have gotten if we had merged these 2 clusters, then all we actually have to do is simply just add the two corresponding clustering features together. Okay, so that's one useful property that the CF has. And then in addition, as we're running the Birch clustering algorithm, or in other words, as we're building this CF tree, while we are not technically storing directly the centroid of a particular cluster, we're not directly storing the radius or the diameter of a particular cluster. The nice thing about the clustering feature of a given subcluster is that there are equations that allow for us to simply just use those three pieces of the CF to quickly calculate what each of these three important aspects might be. So the actual equation for instance, how you might calculate the radius of a given cluster based on the clustering feature is something that I introduced in the practice test. So you can take a look at that equation if you'd like to. But for instance, let's just say we only knew the clustering feature of this particular cluster. So we didn't actually have the data set. We only knew these three elements of that particular cluster. So how could we use this clustering feature to calculate the centroid of this cluster? So what calculation would we use? So you want to remember, this is the number of observations in the cluster. This is the linear sum of the observations in the cluster, and this is the squared sum. Also, we want to think about how we, just use algebra X, Y. Yeah, I mean, so basically, we can simply just take the linear sum of each of our observations and divide, right, by the number of observations, and we get that particular cluster. All right, so we can take the point 4.6, divide by 2, and we get the centroid of that particular cluster. And so we can check, we can double check ourselves that this is in fact the centroid of this cluster here. Right. Okay, questions on that? Okay. So, let's see here. Okay. What am I doing here? So, the way that we, so basically the way that this CF tree is designed is we always have a root node. And, from this root node, we might have a series of non-leaf nodes that emanate from that root node. And then at basically the base of this tree, we have a series of leaf nodes. And so basically each of these nodes in our tree are essentially used as containers for CF entries, which, as we've discussed, correspond to subclusters that we've identified in the clustering structure of the data set so far. So we typically have a set of parameters or additional parameters or constraints that we can specify when building this CF tree. So number one, we can specify, for instance, how many CF entries we'd like to allow in our non-leaf nodes. And then furthermore, we can also specify how many CF entries that we would like to allow in our leaf nodes, basically. And then we can also, our computational memory information might also give us stipulations about how high your tree is allowed to get, essentially. Okay. So let's talk a little bit more about, essentially what this CF tree is actually recording, if you will. So let's actually start at the leaf nodes here. So as we mentioned, a leaf node entry, so basically this is an entry here, what it represents is a particular subcluster that we have currently identified of, observations which have been essentially read into the tree. So this particular CF entry here might correspond to this subcluster that we've identified. And then what the leaf node entry actually contains is the clustering feature, the CF of the corresponding subcluster that it represents. Okay. And then a leaf node, it actually is allowed to contain multiple entries. And so basically what that leaf node essentially represents is a cluster comprised of, multiple subclusters that, so basically it's the cluster that you would get if you combined all of these subclusters represented by each of the CF entries that are contained on that particular leaf node. Okay. And then some constraints, like we mentioned, that we place upon the leaf node entries in particular is that, again, your leaf node is only allowed to contain at most L entries. And then furthermore, each of the subclusters that are represented with clustering features in this corresponding leaf node, each of these subclusters are required to have a diameter or a radius, whichever one you're using, less than T, your pre-specified threshold. Okay. So these are all the leaf nodes. So basically these are what is stored in each of these leaf node entries is basically the smallest subclusters that you will end up seeing in your given clustering structure that you have, that you're identifying essentially. But then as we move up to the parent, so basically we can move up a level in most of these clustering featuring trees. We can move up a level to the parent nodes. So we can actually have, so we have these non-leaf nodes, which are basically in which the entries for the parent node actually correspond to the leaf node of the child. So what that means, a leaf node entry, or excuse me, a non-leaf node entry represents is a cluster of the subcluster represented in the child node that it corresponds to. Okay, so for instance, this entry in this non-leaf node corresponds to this leaf node here. This entry in this non-leaf node corresponds to this leaf node here, so on and so forth. Okay. And so what a leaf node entry contains is very much the same as what a leaf node entry contains. No, my apologies, that should say non-leaf node here. So the non-leaf node entry, not only does it contain the CF of the corresponding cluster that it represents, but it also contains the index of the child node that it corresponds to. Okay. And so basically what this, what an overall non-leaf node represents is the cluster that you would get if you were to combine each of these clusters of subclusters that it's representing here. So we can further go up all the way to the root node. And so this root node actually, is the cluster that you would get if you were to cluster, all of these, clusters of subclusters here, essentially. Okay. And then the final stipulation is a non-leaf node is allowed to contain at most B entries. And then one thing that you do want to keep in mind is that whereas the radius or diameter threshold, or the radius or the diameter of the leaf node entry subclusters can't go above T. However, it is okay for a particular non-leaf nodes cluster. It is okay for this radius or diameter allowed to go above T. Okay, so basically it's only our smallest subclusters which are forced to have a particular cohesion level, essentially. Okay. Yeah, so this is a bit of a lengthy algorithm, but any questions on that? Okay. So for instance, here is an example for how we would construct this CF tree based on 4 subclusters that we have identified here. So, so let's just say, for instance, we have this data set here, and we've added these 8 observations to the CF tree. So if these were the CF entries that corresponded to the, or basically if this was the set of leaf nodes that we have currently created when building this CF tree, this is essentially how we would go about interpreting that. So as we can see here, this CF entry corresponds to this subcluster here. So we can see that it has 3 observations. And if we were to add up all of if we were to calculate the linear sum of this subcluster, we would get this value here. If we would calculate the squared sum of this particular subcluster, we would get this value here. And in this leaf node, there's actually only 1 subcluster that is contained in it. However, in this leaf node, we actually end up having 2 subclusters that are represented with it. So one of these subclusters is simply just represented by 1 observation. So it's this observation here. So it's simply just the point 21. But then this subcluster is represented with this CF entry here. So it's comprised of 2 observations. This is its linear sum. This is its squared sum, so on and so forth. So we have basically 5 subclusters, which are currently represented with 5 corresponding CF entries in the leaf nodes of this CF tree. And so if we wanted to make this CF tree complete, we would actually need to fill in the corresponding information for each of the parent nodes that corresponded to each of these leaf nodes here. So if we wanted to complete this CF tree, we would first create an entry that corresponded to this leaf node with index 4. We would first write the index for the leaf node that this entry is corresponding to. Okay, and basically because there's only 1 subcluster or 1 CF entry in this leaf node, we would actually simply just rewrite this single CF entry here, basically just representing that, this is simply just, the cluster of all of these subclusters is simply just that cluster itself because there's only one subcluster. So we would simply just rewrite that observations CF entry. It's 1.5, 0.5, 1.25, 1.25. Okay. Okay. So I see that it's 4:30. So I am going to pause for just a second. So, okay. All right. So I do see that the emails have gone out. So I'll give you about 30 seconds to check your email. Okay. So I'm going to assume that everybody that is still here was not selected. Again, if you were selected, you do want to make sure that you log off, record your video, and then come back to this content at a later point in time. So someone's asking the question, can you go over what 4 is on the second level once more? Yeah, so this 4 is the index that this entry that we're writing up here corresponds to. So basically this entry here corresponds to this leaf node here. Okay. And so we're also going to be representing this leaf node here with this entry. And so basically what this entry represents, so we would write 5 to indicate that we are referring to all of the subclusters represented in leaf node 5. And so the CF entry that we're representing here is going to correspond to the cluster that we would get if we had merged these two subclusters together. Or in other words, if we had, combined this subcluster with this subcluster. And again, you want to remember this subcluster is represented with this CF entry, and this subcluster is represented with this CF entry. So therefore, if we wanted to quickly calculate the CF entry that would correspond to the cluster that we would get if we merged them together, then all we have to do is simply just add these two corresponding CF entries together. So by adding those two CF entries, we get now a cluster with 3 observations. And if we add the linear sums together, so we get 8 and 3.5. And if we add the square sums together, we get 5.25 and 1.25. Okay. And so again, this is the CF entry, the cluster comprised of essentially merging together these two subclusters here. Okay. And then finally, we would want to fill out the corresponding CF entry in this parent node or this non-leaf node. And so what this would represent, because this CF entry only corresponds to one child node, so what we would do is we would write that this CF entry is going to correspond to leaf node 6, so this one here. And then the corresponding CF entry is basically going to be, it's going to correspond to the cluster that we would get if we were to merge together all of the subclusters represented in this corresponding leaf node. So again, to represent to quickly calculate the clustering feature of the cluster that corresponds to what we would get if we were to merge these two subclusters together, all we need to do is simply just add the two corresponding clustering features of those subclusters. So what we get is now a cluster with two observations with a linear sum of 10 and 2 and a squared sum of 52 and 2. Okay. And so this would be the clustering feature of this overall cluster here. Okay. All right. And so basically every CF tree has to have a root node, or in other words, every CF tree should only have one node at the top. So therefore, we would want to keep this process going and create corresponding entries in the root node that correspond to their two corresponding, or their two child nodes. So child node 2 and child node 3. So what we would want to put here is the clustering feature of the would-be cluster that we would get if we merged this subcluster with this subcluster. So the clustering feature that would correspond to this overall cluster would simply just be the sum of these two subcluster CF entries here. So what we would get is now a cluster that, hold on one second, now has 6 observations with a linear sum of 9.5 and 4, and a squared sum of 6.5 and 1.5. Okay. And finally, we would want to create the corresponding CF entry for the cluster that we would get if we were to combine all of the subclusters that exist in this leaf node. Now it's actually the case that this, this child node actually only contains one subcluster. So it's simply just rewrite that single subcluster here. Okay. This is how we would form a complete CF tree, basically representing the child and parent node relationships that exist between each of the corresponding subclusters, which essentially are represented on the subsequent nodes of each of the trees. Okay. Any questions on that? Okay. So this is a CF tree which has already been partially built. We're simply just, based on the information that we were given about the leaf nodes, we simply just completed the rest of the tree based on essentially what this tree is meant to look like, essentially. However, the actual task of building a CF tree from scratch is actually quite involved. So you can take a look at these instructions, as you're going through the exercises and the practice test, just to kind of look them up. But, for learning purposes, to kind of showcase, how these instructions actually work. What we're going to do is we're going to build a very small CF tree based on simply just these 5 observations here. So let's just say we'd like to, and again, so this is a very involved algorithm. So there's actually multiple phases of the Birch algorithm. So we're actually just going to go through phase 1 of the algorithm today. So we're going to talk about so in phase 1, our goal is simply just to initially build our tree. So we'll focus on that for now, but do keep in mind there's 3 more phases. The last few phases actually are not that complicated. The main complicating part is phase one, which is the task of actually building the tree. But let's just say, for instance, we'd like to build our initial CF tree, in which we're stipulating that our non-leaf nodes are not allowed to have any more than 2 CF entries, and our leaf nodes are not allowed to have any more than 2 CF entries. And then furthermore, let's use the diameter to measure subcluster cohesion. Okay. And so therefore, what we're going to stipulate is the diameter of any given one of our leaf node subclusters is not allowed to be any larger than 3. Okay. And then finally, we're going to use the distance between centroids as a way of measuring the distance between clusters. Okay, so these are the parameters for how we're going to build our tree. So, like we discussed, BIRCH is an online clustering algorithm. So actually, you do not even need this full data set all at once to start building the CF tree. So actually, how we run this algorithm is we feed in each of our observations one by one. So we'll start with this first observation here, so 1, 1. Okay, so what we do with each observation that we're feeding in, we initially represent it as a singleton cluster. So we basically create a CF entry that corresponds to the singleton cluster that we would get if we were to actually have that observation by itself in a subcluster. So someone's asking the question, is this the first algorithm we're learning where we don't have to rerun the whole algorithm after we get new data? Well, not necessarily. So for instance, under the right conditions, for instance, k-means does not necessarily have to be rerun if you get new data. So like we discussed, if your new data generally exhibits the same clustering structure as your old data, then you can get by without actually having to rerun the algorithm. So you can simply just take new observations, assign them to their closest centroid, and still get a pretty good clustering. However, if that assumption is not necessarily met, that technique is not necessarily going to give you the best clustering as more observations come in. So what I would say is that this is the first clustering algorithm that is explicitly designed, if you will, to allow you to iteratively add new observations as they come in. There's no base assumption that you have this set of data that you initially feel good clustering. It's by design, by design, the way that it works is by iteratively adding one observation at a time. Okay. So for instance, starting with our object 1, 1, we would represent its corresponding clustering feature as simply just a cluster with simply just one observation. Its linear sum is simply just the point itself, and its squared sum is technically 1 squared and 1 squared, but that just ends up being 1. Okay, and so in this first observation that's added to the tree, there's actually nothing you really need to do. The tree currently doesn't have any nodes. So basically, this clustering feature becomes the first entry in the root node. So your current tree is comprised of simply just the root node, which at the moment is also a leaf node, because it's both at the top and the bottom. And it's comprised of simply just one subcluster represented with its corresponding CF entry. And just for informational purposes, we know that the centroid of this cluster is 1, 1, i.e. the point itself. Okay, it's not too complicated. So we move on to the next iteration, iteration 2. So we'd like to add this the second observation in the data set, so 1, 14. So what we do is we assume, for now, that that observation is by itself in its own singleton cluster. Okay. All right, and so that would be the centroid of this singleton cluster, and this is the centroid of this existing singleton cluster that we've already factored in. Okay. So the first step is we basically want to figure out what we should do with this potential subcluster. So what we do first is we find the closest leaf node. So starting at the root node, we find the closest entry, the closest subcluster in this root. So it just so happens that there's only one entry, or basically one subcluster in this root node. So in other words, the centroid 1, 1 is in fact the closest centroid to 114, the one that we're basically introducing. So, given that the root node is the leaf node, we've basically found the closest leaf node. So we move on to step 2. So once we've found the closest leaf node, the next thing that we do is we find the closest cluster or subcluster entry in that leaf node. And so again, we only currently have one subcluster represented in this leaf node. So basically what that means is that we temporarily assign this subcluster and this corresponding centroid to this subcluster here. Okay, so once we've found the closest subcluster to this incoming subcluster, we then ask the following question. So, is it possible for us to merge these two subclusters together? So, the answer is no, right? Because if we were to merge these two subclusters together, right, the diameter, i.e. the average pairwise distance of all points in this cluster, would in fact be higher than 3. So the answer is no. Okay, so if we're not allowed to merge a given incoming subcluster with its closest existing subcluster that exists in the tree, the next question that we would want to ask is, well, okay, can we add this subcluster as an entry in the corresponding leaf node that we have selected? And so the answer now is that yes, we are allowed to do this, because that would basically create 2 corresponding CF entries in this leaf node. And that's not above the limit yet of 2 entries. So we are essentially allowed to basically create a new CF entry that corresponds to this incoming subcluster. So our new CF tree would be one in which we have 2 subclusters represented with 2 CF entries in our root node, which is also simply just our leaf node as well. Okay. So very quickly, we can add one more entry to this data set. So moving on, iteration 3. The next observation that we would like to incorporate into the CF tree is the point 5, 5. So again, what we're going to do is we represent that incoming point as its own subcluster. Which we can represent with a corresponding CF entry as follows. And that point has its own corresponding centroid of the point 0.55. And so we go through the same set of steps again. So in step 1, what we would theoretically want to do is we would want to find the closest leaf node to this incoming subcluster here. So given that basically there's only one leaf node, that's, we would simply just pick that one leaf node. And so once we had found the closest leaf node, the next thing that we would do is we would find the closest entry in this leaf node. So basically our incoming subcluster is closest to this subcluster because their two respective centroids are closest to each other. So the next question is, would we be allowed to merge these two potential subclusters with each other? And the answer to that is no, because if we were to merge these two subclusters together, the resulting diameter, i.e. the average pairwise distance of all the points, unfortunately would be above 3. So we then ask the next, can we do the next best thing? Can we add this subcluster as an additional subcluster, or as an additional CF entry in this corresponding leaf node? And unfortunately, the answer to that also is no, because that would basically cause us to go above the maximum number of entries that we can represent in that current leaf node. And so unfortunately, we're going to have to basically do some other things in order to incorporate that point. But anyways, I've run out of time. So we'll get to what we have to end up doing on Thursday. But this is kind of basically how the Birch algorithm starts out. So essentially, we iteratively add each point to our CF tree by essentially going through a series of somewhat complicated steps. Okay. All right. So I'm going to stop there. I'll stop recording.